All right, hello everybody. Welcome back to a new lesson. So this time we are on chapter 6. This first section is called Graphing Systems of Equations. So our focus as we get started with this new chapter, this new semester of notes, is going to be on graphing systems of equations. So we have equations, and systems means more than one in the same problem. So we'll see that as we get started. So in the past, we learned how to graph linear equations, meaning our equations that are just straight lines. Now this time, as we jump into this new section, this second half of the year, we're going to look to solve these solutions that have more than one linear equation in the same problem. So we can determine more than one solution to our system. Of course, we can solve these systems of equations by having a visual image of them. We can draw a graph for each one, and where they intersect will actually be our solution. So you can solve it with an equation or with graphing, as we'll see. So some vocab for this section. We have systems of equations. We have consistent, independent, dependent, and inconsistent. And we will talk about what those mean now. So we should have already had this info down and should be thinking about it. As we start, there are 3 different scenarios to consider. The first is where there is one and only one solution. Now every solution is marked by when our lines intersect. So our graph with one solution looks like this. They intersect at one point, as we see here with the red and the blue line. We call this consistent because there is a solution. And we call it independent because there is one and only one solution. So if you think about a person who is independent, they can handle themselves well on their own. So independent, if you think of on your own or by yourself is one, only one solution. So independent, one solution. Consistent is the word that tells you there is an answer. So yes, there is a solution. And how many? Just one. So one solution is both consistent and independent. One solution. Now the second type of answer that we can have here is an infinite number of solutions. So what does that look like? An infinite number of solutions, we say it's consistent because there is an answer, and we say it's dependent because there are very many solutions. So independent is one, dependent is anything that's more than one. So we have infinite number of solutions that's dependent, so consistent and dependent. Now, if you graph 2 lines that are right on top of each other, it would just look like one line. So that's what's happening here. We have 2 lines graphed right on top of each other. There's an infinite number of solutions. We say it's consistent because there is an answer. And we say dependent because there's more than one. Now, the last type of answer that we see is when there is no solution. So no solution. The word for that is inconsistent. That means no answer. And of course, if we graph 2 lines that will never intersect, there's only one solution, only one way to visually show that, and that is with 2 lines that are perfectly parallel, as we see here. So those are the 3 types of things we'll see as we jump into example 1. So for these examples that we're going to do, you're going to want to have the picture down. Don't worry about the words, but you will want the equations and our images that we see here. So as we get started, let's look at what the question asks us to do. So first, let's read. Use the graph to determine whether the system is consistent or inconsistent, and if it is independent or dependent. So we have to remember what those terms mean and then apply those. So we see if we were to graph both of these lines, and that's back at the first semester work that we did, if you can successfully graph both these lines, then we can compare them. So do they intersect? Well, looking at our graph, we see they do not. So consistent or inconsistent. Is there a solution or is there no solution? Well, since they never intersect, we know there is no solution, so we call that inconsistent. So that is the first half of our answer. So we'll have that part written down. And is it independent or dependent? Well, independent means one solution, dependent means many solutions. So how many do we have here? Well, we have none, so it is neither independent or dependent. It can't be either one of those because there is no solution. We'll just say one thing, and that is inconsistent. Let's double check that. There we go. Since these graphs are parallel, there is no solution, so the system is indeed inconsistent. Now let us look at example 1b. So draw yourself an image of this picture as we have our two lines intersecting. And let's think about what term applies here. So let's look at the first one. Consistent. Is there a solution or is there no solution? Well, we see one solution here. So we have one solution. So that tells me, is it one or the other? Well, in this case, it is consistent. That means there is an answer. So we know that part is true. Now, what about independent or dependent? Well, independent means one solution. Dependent means infinitely many solutions. Since we see only one solution here, the red dot that I drew us, we know our answer then is independent. Remember, independent, like a person who is independent, is somebody who's strong on their own by themselves. So by themselves, by ourselves here is one answer, only one. So consistent and independent. And let's confirm that. And that is true. The graphs intersect at one and only one point. So there is exactly one solution. And our system we can call consistent and independent. So please make sure as you're writing this down, you have yourself an image of these two lines. They cross, they meet at one point, and we call that consistent and independent. This is the scenario that will come up most often, so it is useful for you to remember both consistent and independent for the work that we do in this chapter. So have all that as we jump into the next one. We're rocking and rolling. We're working through these materials, getting started with our second semester on the right foot. Now here's 1C. So you see we have a lot going on in this problem. So as we're getting down our image, let's think about what we're asked. So use the graph to determine whether the system is consistent or inconsistent, and if it is independent or dependent. So let's look at the solutions that we have. So we have a solution here and a solution here. Okay. But we notice we have 3 lines rather than 2. So let's think about what's going to happen here. So we can call this system consistent and independent. So it's consistent because there is a solution. And it's independent because there's only one solution for each pair of lines. So let me explain that quickly. So this dot is a solution, but it's only a solution for this line and this line. And then this dot is also a solution, but this is only a solution for this line and this line. So we have 2 lines that are solutions, but they're independent of each other. In other words, there's never a point where all 3 lines meet. So these are independent answers. They're 2 different answers for different sets of lines. So we can say it's consistent because there's an answer, and independent because there's only ever one for each pair. So consistent and independent. So have those words in a graph that has 2 lines going up to the right, 1 going back to the left. If you have the equations, that's great also. We want to use the terminology to understand what's what in our graphs. Practice those terms. If we can understand those, we should be okay as we move forward. Now 1D gives us another interesting problem to think about. So in this case, is our graph going to be, as we're writing it down, consistent or inconsistent? And is it independent, meaning one solution, or is it dependent, meaning more than one? Let's think about that. So as we look at our graph here, we see if we compare just these 2 lines, y equals x plus 4 and y equals x plus 1. So let's highlight that. So y equals x plus 4 is this one. and y equals x minus 1 is this one. So if we compare just those two lines, which of these terms apply? So if I'm looking at this line and this line that I circled, is there a point where they meet? Well, they both have a slope of 1, and they're in different spots here in our graph, so they are parallel lines. They're parallel. Since those lines are parallel, will they ever cross? The answer is no. So there's no solution. And what's our word for no solution? Well, it's inconsistent, right? So anything that says consistent we know would be wrong. We can determine it. And since they never meet, we know they're inconsistent, and we can't say that there's anything dependent or independent because there's no solution. So inconsistent is always left by itself. That's the only thing you can say. Inconsistent, since these lines are indeed parallel. So you can have that down for 1D. We've practiced those terms. Hopefully that makes sense. We've done 4 examples on that stuff. So make sure you have that picture. For 1D, we say inconsistent, no solution. Now, how about an example 2 type problem? So this time we're asked to solve by graphing. We can graph the system of equations. So we're given 2 lines, we'll have to draw a picture. And we can determine whether the system has no solution 1 or infinitely many solutions. If the system has 1 solution, we can also name it. So we're going to look at these 2 and draw a picture for those. So let's think about what we would do here. The idea is to graph each line. So we know if we have y equals mx plus b, we know, hopefully, because we've done this a ton, and we said from the very beginning of the year this wasn't going away, the number in front of x is my slope, so a slope of 2. And the number added at the end is my y-intercept, where we cross the y-axis. So if we look at a y-intercept of 3, would be 1, 2, 3, and a slope of 2 tells me to go up 2 and over 1. That will get me here. If you were to draw a line between those 2 points, that's how we get this line. And it turns out that this second line here is actually the same as the first line. And let me prove to you why that is true. So if we have 8x minus 4y equal to a negative 12, and we want to solve this whole thing for y. So if we subtract 8x from both sides, let's do that. What will we get next? Well, we would get negative 4y is equal to negative 8x minus 12. And now we want to divide away our negative 4. We have to do that everywhere. So if we do that, what is y equal to? Well, y is equal to positive 2x plus 3. So this equation is the same as this one. So in other words, these 2 lines are the same. If you graph both of them, they're right perfectly on top of each other. And now we can answer the question that we're asked. So is there no solution? Do they never cross? Do they cross once? Or do they cross infinitely many times? Well, the answer, since they're right on top of each other, is infinitely many. So the solution has an infinite number of answers. And we can double check that. Why do we know that's true? Since the graphs coincide, there must be an infinite number of solutions to the system. The 2 lines are the same. So make sure you have down infinitely many for 2a. Now 2b, by similar logic, we can try to solve this one. So the first thing we're going to have to do is solve each equation for y, and then we can compare them. So if I have x minus, and we should be writing this down, 2y equals a positive 4. Now I need to get my y by itself. So subtract x from both sides. I know that negative 2y will equal negative x plus 4. And now I must divide away the negative 2 everywhere. So if I write this in slope-intercept form, it will be y equals 1/2 x, or x over 2, minus 2. So that's one of my equations. That's this one when you simplified it. Now how about the second one? Let's look at that one. So let's rewrite this whole thing for y. So subtract away the x on both sides. We will now get our next step. Negative 2y is equal to a negative x, and hopefully we're writing this down, minus 2. If we divide everything here by negative 2, our slope-intercept form will be given on the next step here. So y equals 1/2 x plus 1. Cool. So we have those two equations down, hopefully. Now we want to look at those and think about a couple things. So if we graph these two lines, what kind of lines are they? Are they two lines that are the same? Are they two lines that are parallel? Or, more interestingly, are they two lines that intersect only once? So what do we see? We have the slope of 1/2 in both lines. Since those slopes are the same, it's only going to be one of two things. Either they're right on top of each other, they're the same line, or they're parallel lines that will never touch. Since the y-intercept here is 1 and the y-intercept here is a negative 2, those intercepts are different, so we have two lines with the same slope but in different places. We call those parallel lines. So these lines will indeed be parallel. And that's proven with our graph here. So draw yourself an image that looks like this of these two lines. Now think about what number of solutions do they have. Since they never intersect, what do we know about our graph? It has no solution. So our answer, the graphs are parallel, they never intersect, and since there are no solutions to our system of equations, we are done. So we can just say no solution to our graphs. So draw your lines, make sure they're parallel, and you can just say no solution. So 2C, similar logic. Our system is already graphed for us, so we'll start jotting down that picture. It's our job now to determine what number of solutions it has, and then name that solution if there is one. So hopefully graphing these lines is not too hard for you to do. Let's quickly just work through why we're able to graph these the way they are. So our slope is 2 for the first one, and it has a y-intercept of 3. So y-axis, it intersects at 1, 2, 3. That's this point. It has a slope of 2, so go up 2 and over 1. That would allow us to generate this line right here. If we looked at this one, it has a y-intercept of 3 as well, so we go up 1, 2, 3. It has a slope of 1/2, so that means go up 1 and over 2. So up 1, over 2, that would give me this point. That's how I would generate this line. So hopefully that part is understood as we practice that. Now you got to think about where do they intersect and how many times. Well, they intersect just once at this point, which is 0, 1, 2, 3. So that's the point 0, 3. Now the point 0, 3, in a graph, it is where the lines intersect. In terms of algebra for our equations, this point represents a solution. It is a solution to the equations. It is the answer that is true for both of them. In other words, x can be 0 and y can be 3 in either one of these equations, and the answers would be the same. They would balance out on left and right. So what do we know if we look at all these? Where no solution is not true because we just said they intersect here. Infinitely many is only true when the lines are right on top of each other, so that's also not true. We do have one solution, but it's not at 3, 3. We said it's at 0, 3. Because 3, 3 would be over here, which is not the case. So our answer is one solution at 0, 3. That is letter choice A. So have yourself the image. Our answer, 1 at 0, 3. Good. So as we work through this material, it's only going to get more complicated as we go. So you got to take down the notes, not only for your notebook grade, which is very important, that caused many people to fail first semester, but as we write down the notes, we can remember the material easier, we can perform better when it comes to quizzes and tests, and start our semester off on the right track. Okay, 2D. We're going to follow the same process here to think about what's what. So we can draw ourselves a picture. Now what do we see? Well, right away, we know these two lines are parallel. Since they are parallel, we know they do not intersect. And since they don't intersect, we know there is no solution, right? There's no point where these two lines intersect. So we know there's no solution. So as we look and we draw ourselves a picture, we see they never intersect. The space between these lines will always be true since they're parallel. So, as we look at our answer choices, we see one solution has to be wrong, infinitely many is wrong as well, and there's not one solution. So our answer must be B. There's no answer that makes those two lines touch. So 2D, answer choice is B. We'll have down our picture with the parallel lines, and what can we say? Only no solution. Now the other word that we're using for no solution that we learned at the beginning of this lesson is inconsistent. So those are interchangeable words to describe that situation. Inconsistent means the same thing. Okay. Double check, and that is correct. All right, awesome. So here's a real-world example for us to look at. So we'll describe the same kind of material, but with a little bit of context. So don't write down the words, just wait for the equation, and we'll talk about it. Okay, so we're talking about bicycling in this case. So Naresh rode 20 miles last week and plans to ride 35 miles per week. Diego rode 50 miles just last week. In the future, he plans to ride 25 miles each week. So our goal now is to predict the week in which Naresh and Diego will have ridden the same number of miles based on their rates and how much they're going to ride in the future. Okay, so that whole paragraph can be rewritten as two equations. The number of miles they already rode, or the number of miles they will ride, we call that Y, will be equal to the number of miles they ride each week times the number of weeks that go by plus the number of miles that they already rode. And here's that scenario. So Naresh is going to ride 35 miles times each week, plus he already rode 20. Diego is going to ride 25 miles each week, plus he already rode 50. So these are the two equations that we can pull out of that whole paragraph. That's the part that's hard. Once you get that, the rest of this is just graphing like we've already done and just applying it, but in a little bit of a new way. So there's our two equations. That's the part you need to write down. From there, we want to try to generate a picture of those two lines. So we know our slopes based on what's next to x, and we know our y-intercept based on what number is being added at the end. So if we were to graph both of those, it would look like this. Now notice something interesting about the graph, and this has come up a lot in our real-world problems. We only have a graph that shows the first quadrant, that is the upper right quadrant. Now why is that the case, you might be thinking? Well, in the case of real-world problems concerning distance, we can only have a positive distance, right? It's impossible to ride a negative number of miles. You can ride no miles or some, but you can't ride a negative amount. So we're only looking at positive values because that's the only thing that makes logical sense. So given that, we're only going to be in the top right quadrant of our graph. So instead of it being a plus sign where we're looking at the axis and we have grouping data all over the place, we only are interested in what's in the top right. That being said, if we graph both of our lines, they would look like this. And now to answer the question of at what time would both bicycle riders have ridden the same amount of distance, what would that look like on a graph? What point? Well, if you're thinking it's the point where the lines intersect, you are right. So that point looks like it's right here, is where our graphs intersect. We can call that point 3, 125. So what does that mean in terms of our graph? Well, what did we say this was? Well, x was weeks, and our y-axis was miles, if we remember right. So after 3 weeks, they've ridden the exact same number of miles. So that answers our question. We can double check that those values are true, and we see they're balanced on both sides. So what do we know? Well, at week 3, both Naresh and Diego will have ridden the same number of miles, in this case, 125. So have yourself both the image of the graph, the two lines going up to the right. They intersect at about 3, so make sure you just have an image that looks something like that. And then we want to say in words that Naresh and Diego will have ridden the same number of miles after how many weeks? That's the important part. We want to say after week number 3, or 3 weeks. All right, same number of miles. If we can understand that, the rest of this section should be pretty straightforward as we look to graph these systems and practice as we move forward into our second semester.